So I will first present the outline of this presentation, the introduction and motivation of my work, and then the data set that I use, the ancillary data, ground data, and also SAR data multi-frequency at CX and KU band. And then I will show the analytical radical square model used for the vegetation, and then the model will be validated, and the sensitivity analysis will be performed. Validation, I've been done with the data already before presenting before. Then I will show you an example of retrieval with the combination of the data and the model. And then the conclusion. So the background of this presentation is the core H2O study on the X and KU band, the sensitivity of the snow from cell data at these two frequencies. And beyond open areas, the retrieval in forest regions have been investigated. The possible contribution of the C-band together with the X and KU band have been studied. And C-band is insensitive to dry snow, but can provide some information on soil properties, freezing to state, which is useful for the snow mass retrieval. The objective, the aim of this research is to investigate on the impact on the vegetation in the retrieval of the snow parameters in a multi-band configuration. So experimental multi-frequency data in CX and KU band have been collected in Finland, in a test site in Finland, and the radial transfer model able to simulate the scattering from vegetated snow-covered terrain is developed and implemented, and the sensitivity analysis have been done. The model, and finally compare with the data. So let's see now the test site is located in Sodankila, which is 120 kilometers north of the Arctic Circle, with the polar and subarctic climate, and which is close to the location of the Finnish Meteorological Institute Arctic Research Center. The three main land-covered tiles are boreal forest, lakes, and peatlands. There are a lot of ground data here, and in a continuous time series. Let's see some ancillary data used to validate the model. The 3-8 map, ladder scan digital elevation model, and the derived canopy closure on the top. You can see that the canopy closure cover fraction, the average value is around 0.5, so the forest is quite sparse, and then the 3-8 average is about from 8 to 10 meters. Then we use the Colleen land cover classification to mask out the other areas, like urban areas, agricultural areas, and water bodies, and also forested areas and open areas have been processed and taken into account. Here, the radar dataset are three band, radar set 2, terrestrial X and SNOSAR, with radar set 2 have 33.2 incidence angle, and we have 10 dates. Terrestrial X, we have 23 dates every 11 days. X band, dual pole, and almost the same incidence angle. And then there's SNOSAR, which is an experimental airborne SAR. We have only 2 days in February 2012. We can see the streaks here. We have only 2 days. The circle is the test area. Here you can see some radars at images in the temporal series. In the red box is the test area, and you can appreciate different level of backscattering in the 2 December, and this is correspond to a change in soil moisture. and in the changes on the ground. And the other images as level, the scattering level is always stable. Terasyl X images, you can see the variation of the scattering and also the V and VH polarization. And also in this case, we have a variation in soil moisture and change in the soil temperature, and a big changes on the scattering depends on snow accumulation, but not so high level, not so sensitive. Here we have the C-band time series for forested areas with cover fraction 0.3. We have almost stable temporal series except one point, which is due to the less scattering increase, which is due to the higher soil moisture. You can see in the brown line. And even for VV and VH polarization. The same for X-band in the forested areas. VV and VH polarization are almost stable and hasn't been affected by the snow depth so much, but the changes are due to the different dielectric constant of the soil and changes on the temperature and the soil moisture. Here is sensitivity to cover fraction at C-band. We have 8 dates for VV and VH polarization. The scatter plot have high sensitivity to cover fraction for both polarization. Here we have X-band, 15 dates for VV, both VV and VH polarization. You can see how the sensitivity decreases with increases the band, the frequency, and because of the lower penetration. And for the 3 dates, VV and VH polarization, the KU band, here the sensitivity to cover fraction is less than the previous case because of the higher attenuation of this frequency. And now we will present the model that we have used to validate and validating that data. The forest is multi-layer radial transfer model with multi-layer medium over a rough interface, soil and snow. According to forest characteristic, each layer is constituted by an ensemble of cylinders, trunk or branches, and spheroids for needle and leaves. Here is an example of the input that we have used. We have used 9 meter height, 3 heights. We have divided the height in 4 different layers. The first layer is the trunk layer, and then the other 3 layers is the canopy layer, which have been divided in the different kind of scatterers. And each kind of scatterer we have measured, and with the dimension and the angular orientation. And other information like dielectric constant have been taken by literature, and dielectric constant changes depending on the season, winter and summer dielectric constants. Here is the scattering model for vegetation. You can see that for close canopy, the contribution of the best scattering, the one that comes from the crown, the one that comes from the trunk, the interaction with the soil and trunk, and the soil and the crown, and the soil attenuated by the canopy. In the case of sparse forest, which is the case of Solankila, the total pixel is divided in the vegetated part and the contribution from the bare soil and the contribution from the soil attenuated by the vegetation, which is here in the shaded area. Here there is the sensitivity to frequency from the model. You can see that the scattering increases when the frequency increases, and for VV and VH polarization, this is for lower biomass, 40 ton sac per hectare. increasing the biomass, the vegetation component increase. You can see here that the vegetation level is higher. And then when we are in the KU band, when we are in higher value of biomass, the vegetation components gets higher. This vegetation component is the value relative to the vegetated part. Here we have the sensitivity of the model to forest and the soil properties. We have the sensitivity between pH polarization. Here in this case, with pH polarization to SWI, no water equivalent. And you can see that in KU, especially in the KU band, you have higher sensitivity to SWI and decreases when the cover fraction increases. The same in X band, but the sensitivity to SWI is lower. Here is the VD polarization. On the left KU band and the right the same X band. And we can appreciate that, you can see that below that when the cover fraction is higher than 25%, the sensitivity to SWI tend to disappear. And this is a problem for the retrieval because we can't consider cover fraction higher than 25%. This is the model validation, radars at C band with the data previously presented. You can see a good agreement with the data for some date. And the same for X band, the same incidence angle. We have a good agreement with the data. Here, KU band, we have a good agreement, but then for higher cover fraction, the agreement is less because of the limit of the validity of this rate transfer model. Here we show an example of an application using the model and the data at X and KU band, and we can see the retrieval. The retrievers know that in forested area, and you can see that the retrievers know the measure are almost the same value, like 37 millimeter and 41 millimeter. In conclusion, with the purpose of investigating the capability of the SWI retrieval in vegetated area, a multi-frequency analysis of SAR data collected in boreal forest was performed. In order to interpret the data in electromagnetic model was developed and was validated with the data. The sensitivity to SWI disappears when the cover fraction is higher than 25–30%. The model simulation is in the full agreement with the experimental data and uses the model the SWI retrieval is feasible in forested areas.
Actually, C band and X band cannot penetrate the vegetation for retrieval of snow water equivalent. So what do you think of your validation?
Okay. So C band can penetrate X band, but the penetration is lower at X band. So the retrieval of snow is possible when the cover fraction is higher, is lower than 25% because of the higher contribution and higher accumulation of vegetation. So there's no FDC can be distinguished in the sensor.
So means are you getting that signature from snow in C band?
Yes.
Like when you are being transmitting through vegetation, are you getting that you are recovered that signal from snow? That again, so it will give volume scattering from snow layer. you are getting volume scattering from the top of the vegetation, peak of the vegetation. Then again it will transmit it to sun.
Yes.
So how are you differentiating?
From C-band and X-band?
No, you are getting signal from vegetation and also you are getting signal from sun. So if suppose you have your model getting volume scattering from vegetation layer and also you are getting volume scattering from sun. So how are you differentiating volume scattering from vegetation and volume scattering from sun?
Here is some. Okay.
You see that this
without vegetation, which is this.
the IGARSS sensitivity to heat, and then with the higher fraction sensitivity to here. So the canopy have an impact on the mask the signal coming from the smoke. And for example, if you have second value here, you have the signal, the difference because between the line is more constant here, this point.
I think this means it can be done only like sparsely vegetated area only,
Yes,
not in a dense
yes,
vegetation. Okay.
Yes, please consider that we are talking about the boreal forest,
Okay.
so very sparse trees.
Okay.